Thanks very much. It's nice to be here. Thank you all for coming. It's great to see so many familiar faces and in general to see so many faces. So I'm gonna talk about climate change with particular reference to the American Southwest. And I'll start by just asking, does anybody know what this photograph was in the news in just the last couple of weeks? Does anybody know what was going on? Exactly. This is a shot of a train being loaded with snow, I think somewhere near Fairbanks, maybe in Fairbanks, and the train is about to haul 7 gondola cars of snow south to Anchorage so they can put the snow out on the snowless main street of Anchorage for the start of the Iditarod sled race. Next slide, please. And here's the reason. Alaska's very warm this winter. This is just from December, I'm going to be showing a lot of graphs and charts and so forth, and I hope they don't drive you crazy. All of them are interpretable, but it takes a little while. Anyhow, this is the temperature anomaly. That is to say, the deviation from the average since last December. And so these areas that are the strongest color are 10 to 12 degrees Fahrenheit above the average. And every part of the Iditarod race was at least 6 to 8 above average. In addition to being warm, Alaska was also uncommonly dry. There wasn't much snowfall. So next slide. This isn't the first time this has happened to the Iditarod race. This is from 2014, the Iditarod. And mind you, we're in deep winter still. At least in Alaska, we should be in deep winter. The problem that they have right now with the race is that the dogs overheat. Those dogs do best in sub-zero conditions. That's what they train for. And these balmy conditions are really threatening to them. So they tend to race at night when it's cold and hole up and rest during the day. Next, please. And this is a heat map of Alaska back in 2014 when it was even warmer than it is this year. By this color through so much of Alaska, I would say that's at least 15 degrees above the long-term average. Next. And that's not the only weird thing that's happened in the Arctic this winter. Check this date, December 30th. This is within 8-9 days of the shortest day of the year, which is to say no day at all at North Pole, just darkness, a little glow on the southern horizon of the sun, but midnight, even at noon. The air temperature at a buoy, proximate, the closest buoy to the North Pole, the air temperature moved above freezing for the first time ever recorded on December the 30th of 2015. Next. So what's going on with our beautiful blue spaceship? You all know, I'm just going to go over some of the kind of physics of the greenhouse effect very, very briefly. But this marvelous thing, this island of life in the desolation of the great void of the universe, is a mostly closed system, but not a completely closed system. It receives a lot of energy, as you know, from the sun. The energy that it receives is shortwave energy, shortwave radiation, which we perceive primarily as light, and which we also experience as heat when that light falls on us. When it hits Earth, that energy converts to long wave energy, long wave radiation, and a lot of it is radiated back into space, but not all of it. A lot of it is trapped by our atmosphere. And in the chemistry of our atmosphere, and this principle has been known since the late 18th century, but experimentally proven only beginning in 1958, increasing levels of certain gases in the atmosphere trap more and more of that long-wave radiation. The chemical we know most prominently in this category is carbon dioxide, but other chemicals, other gases, have a similar or even more aggressive effect, one of them being methane, whereas I love to hear British say it, methane. Next. So, 1958 I mentioned. This is when atmospheric carbon dioxide began being measured systematically. And the result of that systematic measurement is called today the Keeling curve, after Charles David Keeling, who in 1958 was a postdoc from Caltech. And one of the things he did in getting his PhD was to devise a mechanism for measuring atmospheric carbon dioxide. Once he got out of school, got a postdoc fellowship at Scripps, I think it was, and took his machine, actually sent his machine, he wasn't physically there, to Mauna Loa on the island of Hawaii. Got it set up at an altitude, I can't remember, 10 or 11,000 feet. Way up there where the trade winds are mixing the gases, mixing the atmosphere of planet Earth. And he began to measure atmospheric carbon dioxide. When he started, his first measurements were in the range of 313 parts per million. And pretty soon he discovered two things, two interesting things. One is that atmospheric carbon dioxide varies through the year. Why? Nobody knew that until then, but that's what the data were saying. Why would that be? Well, think about it. Most of the landmass of planet Earth is in the northern hemisphere. Therefore, most of the vegetation of planet Earth, the terrestrial vegetation, is in the northern hemisphere. When that vegetation is in full growth, it's pulling carbon dioxide out of the atmosphere. And so our planet's carbon dioxide is lowest at the end of the growing season. Then the plants, so many plants, not all of them, but so many plants grow dormant. They stop pulling carbon dioxide out of the atmosphere, and carbon dioxide rises until the beginning of the next growing season. So you can think of this as a respiration of the planet. It's a gas cycle, an annual gas cycle in the life of the planet. Well, the second thing that Keeling almost immediately recognized is that annually CO2 measurements were increasing. And you can see how they have increased. I downloaded this, and those of you who are teachers, just Google Scripps CO2, and you can get into a website that has all kinds of great visuals and stuff. This is just a couple of days ago. What are we, the 10th? 3 days ago. It was measured, atmospheric CO2 was measured at 403.71 parts per million. I actually visited the observatory, the measuring station on Mauna Loa in 2010, and I remember seeing the real-time measurement of CO2 on that afternoon was 389 parts per million. So it just keeps going up. Some of you have heard of a great organization called 350.org. It takes its name from the idea promulgated by James Hansen, one of our greatest climate scientists, that we're probably really safe in maintaining the current climatic conditions on Earth if our deviation above 350 is brief. We need to bring atmospheric CO2 down to 350 or lower, says Hansen. And so that's where 350.org get their name. Well, you can see we're on a rising scale. Has it always been this way? Is this just a return to another high level that we experienced sometime in the past? What about before 1958? Next slide, please. If we go back to before the beginning of the Industrial Revolution, to 1700, and we can do this through marvelous science, which involves capturing air bubbles in glaciers, in snowpack, in Antarctica, in Greenland, and other frozen places, and then analyzing the air that was trapped in those bubbles thousands sometimes of years ago. And so the gas bubble, ice core data from ice cores, the gas bubbles in ice cores, show us that previous to the Industrial Revolution, we had CO2 in the atmosphere of about, 273 parts per million. Can we go back farther than that? Well, yes, we can. Next slide. If you go back 10,000 years, 10,000 years, look at this consistency, and then look at us. Boom. If you saw the movie An Inconvenient Truth, it was showing these data when one of the most dramatic moments, when Al Gore is being lifted by a forklift to get up to where the graph was going. I don't know if you remember that. It's a great moment in the film. But this tells us a number of things. First of all, this is the period from about here to about there that we call the Holocene. That's the geologic epoch in which all human civilization has developed. And human civilization has really only developed in the last several thousand years, let's say since 2,000 years before the current time, or a little bit more than that. So one of the reasons human civilization, one of the probable reasons that human civilization has been able to develop is the consistency of Earth's climatic regime. So one of the things that scientists are talking about today is perhaps at this point we began to enter a new geologic epoch, which they are calling the Anthropocene, human-influenced, Anthropocene. Anthropocene. Okay, we can go back even farther than this thanks to those ice cores. And what does that tell us? Well, it tells us that our period here is an anomaly in the history of the last 800,000 years. These variations, I can't tell you what all of them are about, but imagine that periods of glaciation, ice ages, all kinds of different things have happened in the last 800,000 years. But this is remarkably consistent. These big variations probably have to do with variations in the Earth's orbit and so forth. There's some irregularities that cause major climate shifts over the very long time. We know about them, and we can talk about them later if you want. But our period is anomalous in 800,000 years of Earth history. Next, please. And so, has this had the warming effect that our theories would say? Well, yes, indeed it has. And here is a graph of global annual average world temperature. And just think about scientifically the difficulty of coming up with an algorithm that gives you one number, basically, for the whole planet over the course of a whole year. This is really hard math. But it's been done at NOAA, the National Oceanic and Atmospheric Administration. It's been done by NASA. It's been done by the United Kingdom Meteorological Office, that's Met Office. It's also been done at a laboratory in Japan. And what you wind up with is, with all these different labs using slightly different algorithms, they come up with different absolute values, but the patterns are completely consistent from one lab to another. So this is science at work, testing hypotheses, using the data. Do the data hold up? If we do it this way, do the data tell us the same thing as when we do it that way? And the answer is, with global temperature, yes, they do. Climate deniers were saying that in this period, the temperature rise flattened out, and so therefore all this talk about climate change was a lot of hooey. Well, the serious scientists, the serious people were saying, something's going on. Earth is probably storing more and more heat in deep ocean than previously. That seems to be the case, and you can see what's happening with the recent El Niños is the oceans are releasing more of that heat to the atmosphere, and we're getting a spike again of warming. Next, please. So here's my climate change rule number one. It's getting warmer nearly everywhere, and you all already know that. Next, please. There's a lot of ways you can look at that. Oh my God. This is the second time in my life this has happened to me. The other time I was reading a poem. It was even more embarrassing. So you can see that each decade has been warmer than the previous one. That's one way of looking at it, rounding things out a little bit. Next, please. You can look at individual things like northern hemisphere spring snow cover is declining, Arctic summer ice sheet is declining, ocean temperature is increasing, sea level is rising. And interestingly, most of the sea level rise that we've seen so far has to do with the oceans expanding. Water expands a little bit as it heats up. The big thing lurking in the background, and I'll mention this again later, is the melting of the ice caps at the poles, the Greenland ice sheet and the Antarctic ice sheet. They haven't weighed in a significant way yet, but when they do, look out. Next, please. Here's a depiction of the shrinkage of Arctic ice, 1984 to 2012. So you can see that's quite a shrinkage. Here's another heat map. This one is from the IPCC. Anybody interested in delving into climate change needs to pay attention to the IPCC. That stands for the Intergovernmental Panel on Climate Change. I think I got that right. Did I? Okay. It was set up by the UN, the United Nations, in the late 1980s to be the world authority on climate change. And it has been. Because it has such broad representation, and because of its mandate to be very careful about what it says, its pronouncements are actually more conservative than what most climate scientists believe. So you can take what the IPCC predicts as the low end of the range of impacts. Next slide, please. And one of the things that the scientific community has had to do is to ask, okay, is this increase in temperature simply the working out of natural processes on Earth? Is it within the range of natural variation? And can sunspots explain it? Can climatic cycles that are completely natural explain it, et cetera? Well, these studies indicate that natural causes would give us this kind of variation in temperature on Earth. But if you combine natural variation with the predicted impact of greenhouse gases, you get a range of variation that runs like this. And if you plot the actual measured empirical data gathered on Earth, it tracks with human impacts. So there's really no question. People who say the jury is still out are whistling Dixie. The jury is not out. The jury came in a long time ago, but some people haven't liked the verdict, and so they pretend as though the jury has not reported. Next. How do we come up with these kinds of things that you saw in the last slide? Well, that's from modeling. And just as climate denial in many ways reflects the worst possibilities of human character and human endeavor, the science behind climate study, including the modeling, reflects some of the highest attainment of human endeavor. We're going to talk about that science for a moment. But first of all, let's accept the fact that no model is perfect. No model can capture the extraordinary, the truly infinite variety and complexity that actually exists in the world. All models are simplifications. So they're all wrong. But some of them, including the ones we're going to talk about, are highly useful. Next one, please. This is an output of a modeling study, actually the use of several different models, 13 different models and 18 total runs of the models to predict from climate modeling what surface water availability would be worldwide. And this slide, this comes from a paper that appeared in Nature in 2005. I first saw this slide in January of 2006. It was put on the wall of a hotel meeting room in Albuquerque by a climate scientist from University of Arizona by the name of Jonathan Overpeck. And I usually am dozing during hotel presentations. But this one woke me up because I looked here and I thought, oh, holy smokes. If this, I didn't say smokes actually, but if this is correct, then this land that I love so much, this American Southwest, is really in for a lot of difficulty and change. And if this is correct, here is Afghanistan, here is Iran, here's the Holy Land, here's Syria. Anything going on in those places anybody know about? The stresses on world affairs from these kinds of changes, and basically I should have said, this basically tells us that we can expect a decline of, at least 20% in surface water availability by mid-century, I think it is. By mid-century. So imagine a fully allocated system, you take away 30%, what do? Well, you have to make a lot of changes, and it's hard on people to make those kinds of changes. Think about the competition for water over here. At any rate, seeing this woke me up and led me to want to find the guy who was behind the study, who produced that map, and pretty soon I was off on a journey that produced this book, A Great Aridness, which came out in 2011, and one of the chapters in this book is based on interviews with climate scientists, including the author of the study that produced that map, a guy named Chris Milley, at the Geophysical Fluid Dynamics Laboratory outside of Princeton, New Jersey. It's a USGS and NOAA facility, if I recall correctly. Next one. And so I asked Chris Milley to walk me through the modeling business. And he gave me a little tutorial, which I can only pass along in really not much more than a soundbite to you all, but basically imagine the Earth's atmosphere in 3 dimensions, and then imagine cutting that atmosphere up into volumes, little squares that maybe are 100 kilometers on a side. Sounds like a lot, 100 kilometers, but it doesn't amount to very much when you're dealing with the whole Earth. And you fill each of those cubes, which are stacked from the level of the ground all the way to the top of the atmosphere, and you fill those cubes with equations for how that little piece of the atmosphere will act under various circumstances. And then you load those equations with data for a starting point. And then you plug this whole thing into a supercomputer and you run it for a week. And you get readouts. You can run it backwards, and that's what they do first, actually, with the models. They load with the data, and you scientists in the audience, forgive me for oversimplifying, but they load it with the data, say, for the present, something we know, and they run it backwards, back in time, to see if the model outputs conform to things that were already measured in the past. If the model outputs conform to the past recorded history, they think, okay, we got something that works, let's run it forward and see what it tells us about the future. And so the Milley study used, I think, 13 different models and ran them multiple times to get the data they averaged for their for the map for this study. And the reason you have to run it multiple times is that different starting points, different sets of data, maybe your starting point was 1990, maybe in another run it was the data from 1995 or whatever, will give you different outputs. So you have to run it multiple times, average, and so forth. But that way, you get a picture of how Earth's atmosphere will behave with different concentrations of CO2 building up over time. Let's look at the next. And what we find, basically, and this business has been going on long enough that these models have been tested pretty doggone well. And what we find is that generally, the models are, what the scientists like to say, robust in that they hold up to close scrutiny, except, in many instances, in one respect. And that is that the changes predicted by the models are occurring faster than the models predicted. We see that in the recession of Arctic ice. This is what the models predict. This is the average. This is the range of variation, which, as you see, gets broader, gets wider as you go farther into the future. And this is actual measurement. So the ice is receding faster than the models at the time this was generated would have predicted. And the reason for this is that we're constantly discovering more little feedback loops that intensify things. We don't have time, but one of them, for instance, is just how you depict mountains, for instance, and the impact of mountains, how you deal with topography. Let's go to the next slide. Here's another study. This one is a 2007 study, and its author is somebody else I interviewed for A Great Aridness, and his story is in the book, in that chapter with Chris Milley. This is the sum up of an article that pretty well tells you what his point is. Model projections of an imminent transition to a more arid climate in southwestern North America. An imminent transition, a shift to a new normal. He says there is broad consensus among climate models that this region will dry in the 21st century, and the transition to a more arid climate should already be underway. So that was published in Science in 2007. Let's look at the next slide. This is from a study that came out from NCAR, the National Center for Atmospheric Research in Boulder, Colorado, just last month, which basically confirms what Sager was talking about, that weather systems that bring rain are becoming more rare in the Southwest. So the more we study, the more we're finding that the models are holding up pretty doggone well. Next. And one of the hypotheses for why the Southwest should become more arid is here. And I mean, I'm packing too much into too little time perhaps, but right here at the equator, this is where the most heat is absorbed by Earth. And as a result of that heat, the air upwells, hot air rises. So you have air currents rising, they get up to the troposphere, they get up to a barrier and hit that and begin circulating around, northward in the northern hemisphere, southward in the southern hemisphere. Where they come down is roughly along 30 degrees of latitude, and if you look at a map of Earth, you'll find most of the great deserts concentrated along 30 degrees north and 30 degrees south, because this air has lost all its moisture. It rains like crazy in the tropics, in the intertropical zone along the equator, because that hot air cools as it rises, and as it cools, it loses its moisture carrying capacity, so rain falls. And it stays dry and it comes down hot and dry over here. Well, one of the ideas of climate change is that as the Earth heats up, it continues to do what it always did, only with more oomph. Heat is energy, right? The Earth's atmosphere is becoming more energetic as it warms, and so this circulation could be becoming more powerful, and the Hadley cell could be moving northwards. Its descending point, they're called Hadley cells. I don't know if I properly mentioned that. But this circulation may be expanding so that the weather that used to arrive at 30 degrees north latitude tends to arrive at 31 degrees north latitude, at 32 degrees north latitude, et cetera. What are we in Santa Fe, 34? 36? So that's just one hypothesis, the expansion of the Hadley cell, about why the Southwest would get drier with the progression of climate change. Next one. So this is what they call a first-order approximation. It's not completely true, but in keeping with that idea that the Earth's atmosphere is becoming more energetic, the Earth is going to continue to do what it's always done, just with more oomph. It's like, you know, injecting steroids into a baseball player, I guess. So wet places get wetter, dry places get drier. We're a dry place, we're expected to get drier. Next slide. And here's an interesting comparison. There's a lot of water stress in our part of the world, even absent climate change. But with climate change, water stress increases a lot. And there are two reasons for that. One is that precipitation will probably decline. That's what most of the models show. But even if it doesn't, even if precipitation stays steady, higher temperatures mean more evaporation. And not even the United States House of Representatives has managed to repeal the law of evaporation. And the relationship between temperature and evaporation is not linear. Evaporation increases, accelerates more as temperature goes up. So it's a curve, not a straight line. So as things get hotter, they become effectively a lot drier because of the power of evaporation. Next. And how does this translate in the world stage? Well, this is not me talking. This is the National Intelligence Council. Sorry for the bad slide. The intelligence services don't publish their stuff in easily accessed media often. But the National Intelligence Council is a group where the CIA and the Defense Intelligence Agency and the National Security Administration and all the other high-level federal intelligence services come together. And they predict serious global water stress. Again, have you ever heard of any trouble arising in this region? You probably have. So this is why, next slide, the CIA, for instance, has reported repeatedly to the president, going back several administrations, that climate change is a national security issue for the United States. It is a world stability issue. Next slide. And it's not just because of heating and drying and water stress and stress on agricultural systems and the possibility of food shortages and things of that kind. But in keeping with this idea that the Earth is becoming more energetic as it becomes warmer, we also have this hypothesis that extreme events will become more extreme and more frequent. Droughts will be deeper and longer, hurricanes more violent, typhoons more violent, other kinds of storms more violent, etc. Next slide. The National Research Council, that's an arm of the Academy of Science, reported to the CIA in 2012, some climate events will produce consequences that exceed the capacity of the affected societies or global system to manage, and that have global security implications serious enough to compel international response. Well, now that's not the most poetic sentence you've ever heard, but the next slide has a translation of it. And this is from John M. Broder in the New York Times reporting on that particular study. States will fail. Large populations will be subjected to famine, flood, or disease will migrate across international borders, and national and international agencies will not have the resources to cope. Some of the disasters are going to be too big to deal with. That's what they're saying. Next slide. We kind of got a taste of that in November of 2013, if you all remember. Typhoon Haiyan, H-A-I-Y-A-N, the highest recorded typhoon winds yet known, even though recording equipment was spotty in the area. It devastated the city of Tacloban in the Philippines, just leveled it. Next slide. Because of these kinds of disturbances, people are going to move. People will go where they have to go in order to live and get by. Next slide. This is a pretty interesting slide, at least to me. I'm kind of a graphics nerd, as you can tell. This is the diaspora of people from Hurricane Katrina by zip code. Somehow, somebody figured out how to record all the requests for flood and disaster assistance relative to Hurricane Katrina, and then mapped those requests by zip code across the entire United States. So look at how, from New Orleans, from right here, how people spread out. New Orleans is still not back to the population it had, not by a long shot, to the population it had prior to the Katrina hurricane and flooding disaster. But look at that. You'll see that with every kind of natural disaster. Next slide. And we haven't really even talked about sea level rise, but again, this is some really interesting science. It used to be, for this period, proxy records, maybe somebody recorded in a journal in 1840 that the high tide was at this rock on this point of the coast or something like that. So scientists acting as historians have cobbled together from before measurements were really taken information about sea level at various places. Then for a period we relied on tide gauge data. Nowadays we measure sea level from satellites, basically with lasers, I believe, that measure the return time of a beam from the satellite to sea level and back, and measure it so precisely that thousandths of an inch can be measured. It's extraordinary science. And so there's a big range of variability in predictions about sea level rise, mainly because we really don't know how the great ice sheets of Antarctica and Greenland are going to behave in a warming world. But it's going to have a big effect. And when you hear people talk about the sea rising a foot, remember that that's maybe not the most important factor. The most important factor may be how much storm surge increases from that sea that is a foot higher. Storm surges are going to account for a lot of the damage that rising seas impact. And storm surges can be many, many feet in height, as we saw with Superstorm Sandy a few years ago in 2012 or 14. Next slide, please. Again, the Greenland ice mass and the Antarctic ice mass haven't really weighed in yet. The big impacts, when they come, if they come, are yet to come. But the trend is already very clear in terms of what's happening to those ice masses. Next slide. And in terms of putting people in motion, we have a taste of that here in the Southwest. I should imagine most of you recognize what this is. This is the border wall, whose advocates like to call it a fence, but it's really a wall. This photograph was taken in southern Arizona near Santa Rita, near Fort Huachuca. Certainly some of the migration from Central America and Mexico up into the United States is driven by climatic change. Teasing that factor out, isolating it from other economic factors, NAFTA and a whole bunch of other things, is almost impossible, but it's in the mix. Next, please. Another impact that we're all aware of here is the vulnerability of our forests to fire. This is a shot of the Las Conchas fire in its first afternoon at a time when the fire was consuming 40 acres every second. It's extraordinary. It burnt 40,000 acres in its first 14 hours, if I remember correctly. And finally finished at, 150-some thousand acres. Next slide. Climate change is going to have a big impact, obviously, on the vegetation, on the ecosystems of the planet. And we're already seeing it. You can almost step out this door, if it's daylight, and see that the ponderosa pine and mixed conifer forest of the east face of the Jemez Mountains is pretty well gone now. And you all know these names: Oso Complex, Cerro Grande, Las Conchas, La Mesa, Dome. These fires have burned across pretty much the whole eastern face of the Jemez Mountains. Those forests are not going to come back as forests. They're probably going to come back as mixtures of clonal shrub communities. In fact, clonal shrub is a shrub that can re-sprout again and again from its root and can propagate itself by root extensions. An ecologist friend said, Bill, if you get to have a vote on your next reincarnation, don't choose to be a tree in the Southwest. Choose to be a clonal shrub, like Gamble Oak or New Mexico Privet. Those things are going to do much better. Next slide. I'm trying to go fast here now so we can get to questions. But you can see the trend in fires in the Southwest. Back in the 90s, we had almost none. Things really picked up as we went through the 2000s. And look at the year 2011, the size of these fires. We're talking about broad-scale landscape change at the macro level. Next slide. And it's not just fire. You all will remember the bark beetle outbreak of 2002, 2003. That's changing our forests too. And the next serious dry spell we get, we're having a little break right now. We're having a little wet interlude and a long-term dry trend. So we're not feeling it this year, but look out, it's coming back. Let's go to the next slide. And not just in New Mexico, but beetle outbreaks have been recorded pretty much, it's almost coextensive with forests. There are some forests, some of these little gray areas, these are forests that haven't had beetle outbreaks, but there are not very many of them. And the reason the beetles are a problem when we have climate change, there are really two reasons. One is that things tend to be drier, as we've talked about, and that dryness stresses trees, so they're more vulnerable. And then also, things being warmer, the beetles start growing, getting active, and reproducing earlier in the year with an earlier thaw, and they keep going later in the growing season with a later first frost. And if the winter is also mild, there's not the die-off that would take place when you have really deep freezes in the winter. It's deep, deep freezes that help knock back the beetle populations. When you don't have those deep freezes, a whole lot more of them are available to get started when the weather warms up. Next slide. So here's one study that a fellow put together, a terrific scientist, Park Williams, who used to be at Los Alamos National Labs. He's now working with Richard Sager at Columbia University. He developed the FDSI, the Forest Drought Severity Index. And this is a way of measuring not just heat, but stress on trees, so that you get that evaporative component in there. And according to his modeling, we're going to be traversing the barrier of the worst tree die-offs of the past in the archaeological record of the Southwest. So we're going to see landscape scale, not just in the Jemez Mountains. That's just a taste of what's to come. We're going to see a lot more over a lot more of our landscape. Next slide. And water. Oh, water. This is a shot of Lake Mead behind Hoover Dam. Something north of 30 million people rely for all or part of their water on water that comes out of Lake Mead through Hoover Dam. Lake Mead is our nation's largest reservoir, and at this shot, this is, I think it was December of 2010. We'll see on the next slide. But this was its all-time low at that time, which is right here, and this is where it is right now, right there. So you can see there's an annual up and down. The down is at the end of the water year when the summer is over and water demand, especially for irrigation, slacks off. then the reservoir fills a little bit with winter inflows, then it starts going down again. Well, it was effectively full in the year 2000. And you can see it's like a ball dropping from a cliff. You get some bounces on the way down, but the trend is downward. When it hits this level, 1,075 feet, then a certain shortage sharing regime kicks in, and there are different stages to the shortage sharing regime as it continues to go down. Nobody seriously believes that the shortage sharing formulas that are in place right now are sufficient to assure the survival of Lake Mead over the long term. But water managers point to it as a great achievement in that they got everybody to agree on something for a while. That's kind of like the Paris Agreement on climate change that we'll talk about in a little bit. It's not adequate, but it's a great sign that we got so many entities to agree on as much as they did. Next slide. I was talking there about Lake Mead, Hoover Dam. That's the Colorado River. I'm just going to say the Rio Grande is not in any better shape. And we'll have similar kinds of problems through New Mexico. I would say this, that cities like Santa Fe and like Albuquerque that are connected to the plumbing of big rivers and water distribution systems, as we're connected to the Rio Grande through the Buckman diversion, have a much better future ahead of them than cities that are not connected to big plumbing. And the reason is this. Over 70% of all the water in New Mexico is used for irrigation. And so as time goes on and water supplies get tighter, you're going to see more and more deals between cities and agricultural districts for the leasing of ag water for urban use. Albuquerque will be doing it, Santa Fe will be doing it, Phoenix and Tucson are already basically doing it. But cities like Las Vegas, New Mexico, don't have a big agricultural district right next to them, and they don't really have the plumbing to move water from a big agricultural district. Flagstaff, Arizona is in a similar situation. So as you look in the future, think about that. Next slide. Here's a fancy word. I'm heading into the home stretch here with stationarity. Stationarity is the idea that what happened in the past is a good indication of what will happen in the future. That's how engineers size culverts and drainage ways and so forth. It's based on phrases like a 100-year flood, a 500-year flood. Well, those concepts, every 500 years we've had a flood of about this size. That's stationarity, the idea that the past is a reflection of what the future will be. The author here, again, the aforementioned Chris Milley, and some of you may know Julio Betancourt, who's spent a lot of time around here. They're saying basically that that way of modeling the future won't work anymore because climate change has changed the parameters, has changed the boundaries of the discussion. Basically, stationarity works if climate, soils, and things like that stay stable. If climate is changing, stationarity is out the window. It's like what you read on your stock prospectus. Past performance is no guarantee of future results. That's where we are with the climate. Next slide. And that's where we are in other regions of our life. That's what this gentleman was saying, Mr. Darwin. He was saying that evolution will go on and on and on, and we don't know where it will lead. He was saying that the future had no known and assured address. Next slide. And that irritated and worried a lot of people. The uncertainty of the future is very unsettling for many people, really for all of us, but some of us deal with it better than others. Next slide. We see that in the climate change debate, which has unfortunately been sucked into the so-called culture wars and the political divisions of the United States in a way that it has not done in Europe and in other advanced parts of the world. Next slide. In fact, we are trapped right now in a kind of tragedy which is classical in its character and dimensions. If you think of Othello here as our society, it's not hard to imagine who the Iago is, whispering lies into his ear about his bride, our planet, Desdemona. Here you can ascribe, there are villains in this story. There's a lot of dark money that has funded phony climate research and disinformation in the climate debate. And there are a lot of Iagos clustering in suits on Capitol Hill, you may be sure. Next slide. Here's what they're trying to sell us. 97% of the world's scientists have contrived an environmental crisis. But, lucky us, they're being exposed by a plucky band of billionaires and oil companies. If you buy that, that's just what they want you to believe. Go ahead to the next, please. Here's another look at this, because that message is falling on the ears of a lot of people. Oh my God, I've got so much to worry about. Getting my kid through college, and Aunt Sue is not well, and my stocks aren't doing that well, and my boss is giving me the dickens at work, and I am worried about so many things. Don't ask me to worry about the climate, too. And some people say that human beings are just cognitively poorly equipped to worry about something a threat that's long and slow, like climate change. Give us a bad guy coming over the hill with a club. We react really well. Our adrenaline kicks in. We respond. Boom, we're ready to fight or flee. Climate change is too slow. Next. In fact, you've heard this about the frog in the pot. Well, I'm told by herpetologists that that's a slur on frogs. But it may not be on us. Next slide. Why is this in here? Oh, there's a lot of change already in the world climate system. Even if we do all the things we should do, we're not going to eliminate climate change, not in quite a few generations. Even with much lower emissions of greenhouse gases, we'll still have some change. We've already got about 1 degree Celsius, about 1.8 degrees Fahrenheit in the global system right now. The thing we've got to do is make sure we don't get to the higher range of changes, which would really cook the planet. Now, in Paris, in December, agreement was made to target holding changes to only 1.5 degrees Celsius. So we're already 2/3 of the way there. We've got to put the brakes on really fast to make that goal. And the cuts in emissions that the various signatories to that treaty have agreed to are probably not enough to get us there. But again, emphasizing the half-full part of the glass, it's extraordinary that so many nations agreed on this. And, well, I'm not going to go into my thing about Antonin Scalia and how he has tried to undermine that. But, so people ask me all the time about, are you optimistic about our solving the climate dilemma? I thought about this a lot. I think it's the wrong question. I think there's another question that we should be asking. And sometimes the news is just so bad, people just shut down. They stop listening. We can't stop listening. We've got to stay on this. Next one, please. Let me ask you if you think this is beautiful. I agree. And I think, besides being just visually beautiful, I think in almost any aesthetic system that you can make an argument for complexity as being a component of beauty. If you accept that, if you accept complexity as part of beauty, then think about the billions upon billions of highly complex strands of DNA to be found here and nowhere else. Life on Earth is so complex. Not just at the level of DNA, but at the level of ecological relationships that are more complexity, more perfection of things fitting, of things working. So where I'm going with this is that this is not just a beautiful thing. You can argue almost mathematically that in all the universe, it is the most beautiful thing because of its extraordinary complexity, the diversity of life on Earth. Next slide. And so, one of the marvelous things about Earth is that even as its beauty is eroded by loss of species, by simplifications of landscapes, by a whole lot of things, most of them driven by you and me, Homo sapiens, even as Earth's beauty is eroded, it remains inexhaustible. It remains essentially infinite. And that means that no matter what, down the line, there will always be immense beauty on Earth, and there will always be the challenge of This is Canyon de Chelly, by the way. How many people have been to Canyon de Chelly? Oh, a lot. Good for you. Marvelous place. So the point I was making is that even as the beauty of Earth is eroded, it remains inexhaustible. It remains essentially infinite. And as long as beauty remains, and it will always remain, there also exists for us the call to defend and conserve that beauty. And that, I submit to you, is an invitation to have meaning in your life. The defense of Earth's beauty is as meaningful an enterprise as you can engage in. And I would say meaning trumps optimism. Next slide. The thing to ask is not how will this turn out, but what will I do next? How shall I help? And this is again Canyon de Chelly. This is one of the most beaten up landscapes anywhere. But it's still beautiful. It's still beautiful. Next slide. And so that's our job as people, to steward this planet, to conserve that beauty. And so much rides on what we do. Not just our lives, our kids' lives, our unborn generations ahead of us, those lives, but the life of every creature on the planet. And those creatures, in a sense, are there by the very existence of their lives. They are interrogating us. They're asking us, what are we going to do? How well are we going to perform? Thank you very much.
your presentation this evening. My name is Lindsay Holt, and we've known each other for many years now. In 2013, I spent a little bit of money on a website to educate young people about how we got to where we are with CO2. I spent 2 months doing some pretty serious research, so I think I'm on the same page. There was a gentleman by the name of Dennis Meadows, and he wrote a book called about the balance, okay? And this was in the 70s. And they were funded, oddly enough, by the Volkswagen Foundation. And he predicted in the mid-70s that there were a number of trends that were going to accumulate, and the trajectory was going to keep rising in an exponential fashion, to the point where by the end of the first decade of this century, if we hadn't changed our ways, he said that we would no longer be able to respond to the crisis creatively. We would be responding to crisis after crisis. In other words, what he was saying is that we couldn't choose the direction that we wanted to evolve, that we would be evolving by responding to crisis. So I wrote him a letter, an email, and I said, can I use that phrase, evolve through crisis? He said, by all means. So that was the title of my website. And I just want to say to all the young people here this evening that I agree with your conclusion about beauty, and I think that one key to understanding that is that we're going to have to radically redefine how we look at beauty and how we're willing to accept beauty, because nature really has it in for us in terms of presenting us with new versions of the beauty that we're going to be faced with. And also, I want to encourage all the young people here to please develop your political skills, because the changes that we need to make are not going to happen unless you get out there and get active politically. I travel a lot throughout North America and the western United States, and I've seen all these places that you have slides, particularly between here and the West Coast. And one thing that strikes me, I just drove back from Los Angeles, through Las Vegas by the dam there, and I spent a lot of time looking down on that very scene. The people in Vegas are in trouble, and they're going to really wake up pretty soon. But when I talk about political will, what I'm describing is you have to be visionary, and you have to think out of the box.
You know, it's not a yes or no question. We're going to be able to do a lot of things better than we do now. We're going to fail in some areas.
Yeah.
The question is, are we going to succeed more than we fail? And what's the society going to look like after we pass through this period of transition? I don't think anybody has a crystal ball there. And that's why I say I don't think that the question of are you optimistic about the future or not is the right question. I think it's more about, okay, what am I going to do next? It's a more existential question.
Yeah.
So, incidentally, Las Vegas has a better future than you might think. They're now building, they're bringing online their third intake from Lake Mead, and it's not a pipe that goes into the side of the lake. It's like a bathtub drain. And for good reason, because even when Lake Mead shrinks so much that Hoover Dam stops producing power and stops passing water to the lower basin out of the lake, Las Vegas will still be able to get its water from the bathtub drain. And there's a joke with this too, and that is that it's the top layers of the reservoir that are the most polluted, actually, and they have a lot of chemicals from the drugs that people take and excrete that go in there. And the joke is that in Las Vegas in the future, when they're really sucking down the nastiest water, nobody in that overstimulated city is going to need Prozac or Xanax or any of those mood-altering drugs, because they'll be getting it in their tap water. Silver lining. Yes, sir.
Question for you on predictions. A lot of predictions of the mid-century stuff are out there and stuff like that. And the models, I know they adapt the models as they get real data and correct for them. And the models have collapsed. There used to be about 15 or something in the 90s. Now they're about 4 that you showed. What about 2020 to 2040? There's a lot of conjecture out there about that. Is there any data coming out of the research institutes about 2020?
Yeah, there is. There's more and more, and it depends on the locality. Right now, there's really good stuff coming out of UCLA that is specific to the Los Angeles basin, believe it or not, where the models have been diced up. Instead of 100 kilometers on a side, we're talking 10 kilometers or even 1 kilometer. And they're applying these new slicings and dicings to smaller and smaller areas. So the LA basin has some very specific mid-century predictions now. Richard Sager at the Lamont Doherty Earth Observatory, which is part of Columbia University, and his lab are doing more and more site-specific mid-century predictions.
Nothing from 2020 to 2040?
Well, that's what I'm talking about is mid-century.
Oh, it's not 40 to 60 mid-century.
Well, yeah, you're right. Not that close range, but it's the science is moving in that direction.
Anything being done here?
Less here because of less population and less money.
A really mundane question. A friend pointed out in the sky in the clouds, and there was pink and blue colors on the edges of the clouds, and they said, "Oh, that's methane gas up there." Haven't addressed methane gas, which is a big problem. But are we actually seeing methane gas?
I couldn't tell you. I would highly doubt it, but I don't know.
Yeah, but is the same sort of research being done for modeling being done?
Well, methane is in the models. And, you know, one of the sleeping giants of all this is what happens if the permafrost of the Arctic thaws because there's a lot of methane trapped in that material. And so that's another nonlinear surprise that could be lying down the road. Yes, ma'am.
The official scientific statements of how much the temperature has increased here in the Southwest and in New Mexico specifically would have us believe it's only increased 2 degrees in the last 20 years. But for many of us living here, it feels a lot more like 10 degrees or more. And temperature, you know, following the temperature estimates, it would support that. There's more peak high temps, you know, the frequency of that is much greater even since the year 2000, let alone going back to 1990 or before. Can you address the seeming discrepancy between what we're being told and what we're experiencing?
Well, the temperature increase for the Southwest that's been empirically measured is a little bit more than the world average, but not a lot more. So instead of 1.8 degrees Fahrenheit, it might be the 2 degrees Fahrenheit that you mentioned. But the subjective experience could be magnified, shall we say, not least by evaporation, also by the greater frequency of what you mentioned, extremes. And incidentally, the climate models suggest that there could be extremes of all kinds. Extreme rainfall. I had a slide I took out of occurrence of extreme rainfall events. Those have been increasing for basically every part of the country, even though net rainfall or gross rainfall, total rainfall, for our area has been decreasing. But high intensity events have been increasing too. So it's really a mixed bag. With the increased volatility of the climate, we could have instances where a long drought, a really severe drought, is ended by terrific flooding. In fact, I went through that in Chihuahua at one time with the breaking of their longest drought. I happened to be down there. We hardly could get out of the place. Our gigantic Ford pickup, the biggest pickup Ford makes, we had water coming up over the windshield going through some of the, anyhow. So extremes increase.
So those little 2 degrees could kick off a process that results in greater extremes.
Yeah, I mean, yes, in general, although the causality is murky.
We're going to have to call it a night. Thank all of you for coming. The winning number is number 38. 38. Somebody has to have 38.